Good afternoon, everybody. So, welcome to Inside Azure Innovations at Ignite. How many people have been to Ignite before? Just raise your hands. Wow. How many people have been to more than 10 Ignites? Quite 20. All right, because you're lying, because there hasn't been 20 Ignites. In any case, I've got just a jam-packed session for you this afternoon. If you've seen versions of this in previous builds or Ignites, you know that what I do is show you what we're working on, what we just released, what's coming, science fiction stuff, and hopefully you've seen some of the things that I've talked about actually go into production and you're using them. This session, I think, might be the best Inside Azure Innovation session so far. And you might be thinking he says that about every one. But if I don't think it's the best one, I don't say that. I just do the presentation. But I do think it is. I had to cut a lot of demos just to get this in. So I'm going to be moving very quickly. There's 12 demos in this session. And it spans all of these areas of innovation, from data centers to servers to what we're doing with the compute infrastructure, networking, storage, and then finally confidential computing and cybersecurity. First, though, let's talk about a little about data centers. And what I'm going to do is just put up a slide that's the stats that you've probably seen a dozen times now by now at Ignite, which is 400 data centers, 70 plus Azure regions, tons of cabling. But I actually got to go and tour our Fairwater 2 data center in Atlanta. And it's kind of ironic because a lot of people are like, well, you're the CTO of Azure. Sure, this is like an everyday thing going and visiting a data center. But the last time I toured a data center was our Quincy, Washington data center in 2015. I have not personally been to one until this trip. And I thought I'd show you these pictures that I took myself to walk you through it, because it was a very cool tour. First, I had to dress up like a construction Bob. And it's like infrastructure code. No, this is infrastructure is construction or something like that. But what we did was go up to the facility. You can see it's a construction site, which is why we all had to wear the hats. This is the network cabling that connects the top floor of that data center to the bottom floor with the GPUs. That's the network core of that data center. Here's the bottom where before we put in the racks, the liquid cooling cable's hanging. We got to see a rack get uncrated and actually put into place in the data center. And here's the back of one of those racks. We got to see a break fix. This is where they've got one board. This is the back of the rack with the liquid cooling. And then I saw this. I was like, the group had gone ahead. I saw this hanging. I'm like, this seems like it should be plugged in. So I found the plug and I plugged it in. And like a few minutes later, Scott's pager went off and he's like, oh, we just energized power cell 4. I don't know how that happened. And I'm like, oh, I guess maybe I shouldn't have done that. I kept quiet. I don't think it caused any damage. So one of the things that we're doing with liquid cooling is taking liquid cooling into the servers, as you know. And we've been working on cold plates liquid cooling for a long time. As these systems get more and more heat generative, we need an efficient way to cool it. And liquid cooling lets us pack it densely, lets us cool more efficiently. But we're taking the cooling to the next level. This is cold plates. And what cold plates do is take the liquid through a metal circuit on top of the actual silicon die, whether it's a GPU, an accelerator, or a CPU. Some of us have liquid cooling systems at home that we game with. But with Microfluidics, we take off the thermal resistance off the top of the chip and actually flow the liquid directly on top of it with a very novel way to extract the heat. And the benefits of this, they're just numerous. When you do this, and this is a sideway view of what we just saw, there's these 2 levels here of microfluidics where we can stack chips on top of each other because this is so efficient at removing the heat. And you can see a 3D view of just one of those layers has these micro fins that extract the heat from the bottom. And we have cool liquid flowing in one side and taking it out the other side. This is 2 to 3 times more efficient than cold plate liquid cooling. We can reduce the max temperature of a GPU down to reduce it by about 20 degrees Celsius. And that lets us do things like overclock. It also lets us run hotter water through the system because we can cool so efficiently. But the really novel thing about this is, I've talked about this before at previous Azure Innovation sessions, and I've shown you a little bit about this. We actually have this running now in pilot productions. And this is a picture of one of the first servers with Microfluidics cooling on top of an Intel Ice Lake CPU. This is it blown up, and you can see here the lid taken off that Microfluidics and the etchings directly on the silicon. And this etchings let us extract the heat from the hot spots efficiently. So it's going another level using machine learning to figure out how to get the etching done, kind of inspired by biology, to extract the heat off it. And what I have up here is one of these live. So here's one of them I got in my hand, one of the prototype systems, and then if we switch to the microscope, you can see there the actual etchings of this particular system. And just to show you it's real, I can move my finger back and forth. See, this is not just a projected image, but it's almost like artwork is what it is. And again, completely designed with machine learning algorithms to figure out the best way to etch it. So this is well on its way to production, and I think you're going to see this transform. We're working with our upstream vendors so that instead of us having to do the etching when the die comes to us, it's etched at the fab, and then we can just directly put it into place. So I think over the next 5 years, you're going to see the whole silicon industry for at least high-performance computing and GPUs switch to this. So let's talk a little bit about servers now. And the first thing that I want to talk about is Azure Boost. Azure Boost is the heart of our server infrastructure. I've talked about it many times now at the Azure Innovation sessions. And the idea is going from this traditional architecture where you do all the storage and networking processing right on the server to having an offload card, which is designed specifically for that kind of packet processing or block processing for storage in silicon, either FPGAs or accelerators or DPUs. And our offload card is called Azure Boost. Internally, it's called Overlake. And this allows us to move all of those data plane and control plane components off of the server onto this offload card where they can run more efficiently and not interfere with the workloads that are running on these very expensive CPU systems. We're actually now gone multiple generations into Azure Boost. This is our latest version of Azure Boost. And you can see it's got 2 ports on it. These are 200 gigabit Ethernet ports. And then that die in the middle is a system on a chip, which has an FPGA on it and a bunch of ARM cores on it, running Azure Linux, where we run all of that data plane and control plane software. And one of the things that we can do with this is achieve incredibly high performance. You might have seen numbers before, and I'm going to show you the latest updated numbers with this latest generation of Boost. For remote storage, for example, we're at 20 gigabytes per second, which is a 1.4 increase from just build of this year, and 1 million IOPS, remote disk storage. For local disk storage, for an NVMe direct attached drive, 36 gigabytes per second with 6.6 million IOPS on one of our servers because of Azure Boost. And then the same kind of performance boost with networking. That's 200 gigabit Ethernet ports for a total of 400 gigabits coming off each server, 400,000 connections per second. And because we have got 2 links, they go to different ports in the TOR, or 2 different TORs rather, top-of-rack routers, which means we can service a TOR and have minimal impact on the workloads running on that, and do sub-second updates of the top-of-rack routers firmware without impacting the workloads. And then for security, we're implementing with confidential computing encrypted connections between the CPU and the Boost card, the code on the Boost. You can see what we did here, Azure Boost connected device, ABCD. So just a little play there. Now, and we've been rolling this out for several years. We're at 25% of the fleet now has Azure Boost cards in it. That's a 1.5 increase just from build this year. And 100% of new servers, including HPC and AI servers, ship with Azure Boost in it. Now, taking everything off of the server allows us to offer bare metal instances. And our first step towards bare metal instances is for Azure OpenAI. Sorry, for OpenAI, not Azure OpenAI. For OpenAI, That data center that you just saw, where they're going to be doing a lot of training, that's going to be done on bare metal GPU instances, because Azure Boost will let us control the network and security of the system, but give them direct access to the server. So this bare metal instance, we'll show you a little demo of that in action. This is the Azure portal, and what we're going to do, if you take a look at that size there, it's an ND144, so this is a GPU-based server, metal v6. And I'm going to connect into it just like I would any other Azure VM, except now I'm connecting to the bare metal server, SSHing into it. And you can see here, when we run systemd detect virt to see if it's virtualized, we see none. There's no hypervisor under this. This is the raw metal. We look at the PCI attached devices, and you can see the full list of server attached devices. And one of the reasons that OpenAI wants access to this, and so do our own internal training, is that they can, as an application, know the health of these devices better than we can looking from the outside. So they can look at the Ethernet card and the diagnostics coming off it, or the InfiniBand cards, and see exactly what the health of those systems are, which this bare metal instance access lets them have. But but Azure Boost lets us do other cool things too, because we can offload and we can get very high performance, very controlled and consistent behavior of our network and storage stack. And one of the things that we've done is introduced remote direct memory access to our guest VMs. So RDMA is a transport protocol that is very stripped down and effectively lets you do direct memory access, projecting what seems to be the memory of another system into your own address space right into that, and then it magically gets transported to the other side. So you cut out completely all of those layers in a typical protocol stack, like TCP, including all of the operating system components that are involved with delivering interrupts and processing those packets, to just basically give me the access to the wire, give me a place to dump it in the other side, and now I can do it. And so this guest access RDMA through Azure Boost lets us project this memory effectively into those virtual machines and let them communicate to one another that way. We can use this guest RDMA not just to let virtual machines talk to each other through RDMA, but also to talk to GPUs, because modern GPUs also support direct memory, remote direct memory access, RDMA. So this allows a virtual machine running an AI workload to directly dump information into the GPU or read it out without worrying about networking stacks, even if it's not locally attached. But this is going to blow your minds. RDMA is a protocol that's considered pretty sophisticated, and it requires very little congestion or no congestion to be reliable, and it requires consistency of the latency of the network to also work well. We not only have taken RDMA and stretched it across our own data centers, not just across multiple data centers in the same region, but now we've taken and stretched RDMA across regions. And the benefits you get out of stretching RDMA across regions is, of course, cutting out, again, everything in the middle, getting very consistent performance with low latency, which is really good for AI training workloads. And if you heard, the Fairwater 1 in Wisconsin is directly connected to the Fairwater 2 in Atlanta that we just saw, because we expect that training runs are going to span both of those data centers, not just those data centers, but the other ones we're building around it, to have multi-data center, multi-region scale training with the benefit of RDMA over the WAN. So I want to show you a quick demo of RDMA over our WAN, not even the dedicated training fibers that we connected those regions together, but this is over our Azure WAN. You can see here there's a machine in South Central US and another machine in East US. And we're going to SSH into them, get their SSH addresses here. And then once we're connected into them, we're going to run an in-house RDMA transport performance tool. that is going to show you latency, and it's going to show you bandwidth. And the first thing to note is this is going across from East US, somewhere in the Virginia area, to Texas. And if you take a look at the P50 latency, it's 32.5 milliseconds. You look at the P99, it's 33.31. Less than 1 millisecond variability across the country. And you can see the bandwidth there. The provision bandwidth is 130 gigabits per second. We're driving it with this benchmark close to 100 pretty consistently across the country. So that is the benefit of Azure Boost now taken all the way to the WAN. So let's switch over to compute and let's take a look at the revamp of Azure's compute infrastructure. And the reason that we're revamping is because the traditional architecture for running hostile multi-tenant containers, and what I mean by that is containers that are running code that we don't trust and that you, in your running your own code in Azure, might not trust. We need to isolate them strongly, and we do that with one security boundary in Azure, and that is virtualization. Now, the way that you let a sub-allocator, so our Azure allocator allocates virtual machines, but in the cases of containerized workloads, like Kubernetes, or like our own internal service fabric, they want to allocate containers, and in some cases, those containers are considered hostile. They contain code from third-party customers that we don't trust. So the way that we've done that up to now, if you use Azure Functions, is you've been placed in nested virtual machines. So we introduced nested virtualization into the Hyper-V about 10 years ago. This allows us to put those containers on top of a hypervisor inside the virtual machine. And you can do an inception thing, which is kind of cool. Virtual machine inside, hypervisor inside a hypervisor inside a hypervisor. The downside of that is that you impact performance because you're making transitions whenever you need to go out through those layers of virtualization. So we want containers to be first-class citizens in our infrastructure. We want to give them direct access to hardware. And that means that we need to bring them down and put them on the metal next to the virtual machines that control them. This is what we're introducing. I think this is the first time that we've publicly said what this kind of virtualization is going to be called, and that is direct virtualization, as opposed to nested virtualization. And here you can see that the parent, their partition, which is maybe running the workload orchestrator, is able to ask the hypervisor to take CPU and memory resources and other devices from it and create these children. But these children look like siblings in the sense that they're running on that base server hypervisor rather than in a nested one, eliminating the performance overheads. What I'm going to show you is we've way down this path now, and some of the things we need to do to flesh it out for production or support things like live migration, including live migration of child virtual machines and live migration of child containers. And we migrate the whole pack. That parent that has spun off the children, it gets live migrated together with its children. And I've got a demo here of direct virtualization live migration. Now, the first thing you're going to see on the left side is the root hypervisor on the server. And the second thing you're going to see me do is then go into the parent partition of the virtual machine that is running on that and look at its view. And it will think that it's got two children VMs, even though they're effectively siblings, that the root hypervisor is letting it see. So here we are, and you can see in this nested virtual machine, or this layered virtual machine, you can see virtual machine A and B. They're both pinging the root server, the root Windows operating system. Now we're going to initiate a live migration, and what we're going to see is the live migration of that parent virtual machine with its two children over to the server on the right. And we're going to speed this up because it takes a few minutes to migrate all the storage. And now we're going to look over on the right side. We get VM, and now you can see there's the parent partition that moved over. And if we connect to that, it looks like a virtual Hyper-V host, because inside of it, you can see it's looking at its children pinging the host from there. And we saw that whole thing move with live migration. So that is kind of a raw look at one of the fundamentals, but now we're layering our workload managers on top of it. One of them is Azure Container Instance, which lets you have a serverless container. And now these serverless containers, because they can go on to direct virtualization, can support things like GPUs and InfiniBand. And they can also provide you better performance. So here's a virtual machine with direct virtualization, 2 child VMs that have pods in them. I'm going to show you a demo of the performance difference between nested virtualization on the left and direct virtualization on the right. Here on the left, we're going to run a Postgres PG benchmark. And there's a couple of stats we're going to look at as this thing runs. And the first one is the transactions per second that each one gets. Because we stripped away a layer of virtualization, we go from 860 TPS to 1200 TPS, roughly a 50% boost. And the second thing that we're going to do is do network communication. Again, getting rid of the second layer of virtualization, a SOC perf benchmark that has a client and a receiver. We've got now 4 containers involved here, 1 pair that's nested, 1 pair that's direct. And what you're going to notice here is a reduction in the tail latency. And that reduction in the tail latency, again, happens because we've stripped away virtualization and we've stripped away jitter caused by that second layer of virtualization. So the benchmark's running. And if we go take a look now at the P99 latency, you can see it's 6259, 6.2 microseconds. And you can see it's 1.6 microseconds P99 latency on the direct virtualization. So just benefits all around from going from layered to direct. And I mentioned GPUs and InfiniBand networks. We've not been able to offer containers that have GPUs because we effectively have to give them the whole server to give them the GPUs directly. But now with direct virtualization, we can finally control the device assignments to the children containers. And this is really useful in our Manifold AI infrastructure serving platform, where we've consolidated all our GPUs and accelerators across all of Microsoft and our global Azure fleet to one control plane and data plane that abstracts the hardware, that does congestion control, does quota management, does prioritization. And now we can give Manifold the ability to slice up a server into tiny pieces. Because here you can see an Azure VM with direct virtualization with 3 children containers, UVMs, can take the GPUs that were assigned to that VM and then reassign them to its children, a subset of them or all of them. And to show you that in action, I've got a demo here of Manifold running on direct virtualization. The first thing I'm going to do is get the nodes in my Manifold cluster. And now get the pods in one of those nodes. And you can see there's a bunch of pods. This one is Llama 4 Maverick, which is a multimodal model that knows how to look at images. And then we've got a CPU pod there. And we're just going to look at each of those inside by connecting to them. And you can see that the one that's running Maverick, an AI model, has direct access to all the GPUs on the server. It's got 88 processors. It's got 1.5 terabytes of RAM that its parent gave it. And you can see NVIDIA SMI looks just like any other GPU server. Now, over on the CPU container, you can see that it's just got a gig of memory, and it's got 2 processors. And it's got no GPUs attached to it. These are sitting side by side next to each other. And just to show you this is fully integrated in a Manifold, we're going to take this image of a cat, and we're going to deploy it to the models as a service endpoint to do inference using that pool of Maverick. And you can see it works end to end. So this is what you're going to see in the next year, is really productization of direct virtualization across our full stack. So let's switch over to networking. And there's some amazing things happening in networking. So traditional software-defined networking is, you use offload your Azure Boost policies to this you offload your network policies, your SDN policies, off onto Azure Boost, where they get processed by the accelerators there. But one of the challenges that we have is that there's certain network functions that you want to scale much higher than the capacity available on top of Azure Boost to do that kind of processing. So if you take a look at network virtual appliances, which is what people deploy to do, bump in the wire kind of processing of network traffic, whether it's traffic routing, security policies, flow offloading, ECMP load balancing, those happen in a separate virtual machine today. But what we're doing is accelerating that with network virtual appliance offload devices. And we do that, this is called the Sirius appliance here, the VNet appliance. You can see we can do it full rack, we can do individual blades depending on the scale. And what you can do is connect them as the bump in the wire across not just virtual machine to virtual machine, but virtual machine to private endpoints. And one of the private endpoints that we've been asked by AI training customers is we want our Azure storage accounts to be behind a private endpoint and get really high bandwidth performance to them. So what I'm going to show you is just that, the kind of performance you can get from one of these network appliances by first showing you how we configure one. You can see this is, we're creating a virtual appliance here. You can see 3 sizes, 50, 100, and 200 gigabits. We're going to create a 200 gigabit appliance. And then you can see that we've got actually 5. We just created 1. There were 4 existing ones. We have 5 total. Some of these are 200. Some of these are 100. And you'll be able to see that in a second. Now we're going to go and take the address of that virtual appliance and add it to our ECMP routing rules for both storage, private link, as well as the interface that we're attaching to our virtual machines. So now when storage talks to compute, it'll be going through that set of virtual appliances, equally spread out across them. And this is what's going to let us now get this incredibly high performance. So now what I'm going to do is run this test. This test is going to spin up 20 storage accounts with reading from them concurrently. And you can see this is sped up a little bit. This is the bandwidth up and down over 1-minute intervals aggregated. And then at the bottom, you can see that's the network virtual appliance loads. We've got 4 200s and 2 100s. And you can see there a total of, we were driving right there with 98 virtual machines. We were driving 684 gigabits of traffic to those storage accounts. And that's only possible because of this SDN offload onto these accelerated appliances that you just saw. Now, how many of you do kind of the traditional IT pro functions? You monitor network traffic, you configure a network. Anybody left? Okay, there's a few of you. So those of you that have done it or still do it will be excited to see this. VTAPs, where you want to sniff traffic for some reason. You want to look at, hey, there's a problem in the network, let's go sniff the traffic to see what's going on, or you want to sniff the traffic to see if there's security issues. We've enabled VTAP with this SDN offload as well. And this allows us to put this bump in the wire and take the traffic between a virtual machine and some other destination and route it to the VTAP virtual machine that starts to see it, that traffic sent to it, because the SDN appliance can send it off. And so let's go take a look at that. So here I've got a virtual machine that's going to be where we want to monitor traffic. And I'm going to set a filter for a UDP port. And that UDP port is where we're going to tell the VTAP to send traffic between this virtual machine and this one that are talking back and forth to each other. Now, you can see that they're sending a lot of traffic. We don't see anything yet because we haven't set up the VTAP to point at the monitoring machine. So let's go and do that. And here's our VTAP configuration. We're going to change the destination resource and look at the traffic collector and the port. So this is where we say, hey, start to send traffic to that port on that traffic collector VM. And then we take a look at the sources. and we're going to add both of those virtual machines. So you can see source. So we want to see that virtual machine. We identify it through its network interface. And now you can see suddenly the traffic started flowing. This is the traffic from one of those virtual machines. The other one gets routed to the VTAP that can watch it happen in real time without affecting the traffic between those two virtual machines. So this is kind of really cool too. The scenarios that you can imagine with this are pretty incredible. And one of them that I had to cut, unfortunately, was multicast. Because now we can take the traffic from one virtual machine and use the SDN appliance to spray it across any number of virtual machines, which is awesome for lots of different applications. So let's switch over to talk about storage now. And one of the things about storage is that you're seeing the demand for bandwidth grow. And I kind of showed you that before and talked a little bit about AI workloads. AI workloads, especially these frontier models, when they train, suck a huge amount of data off of storage. Those models are terabytes in size now. And whenever the model checkpoints during the training process, you need to write that back to storage so it's persistent. And that's also terabytes of data. Or if you've got a workload that wants to suck in videos to do training on, that can be terabytes or even petabytes of data. So how do you get a thick, fat pipe into Azure storage to do that? And that's for training. We talked about inference too, loading the models. Models are loaded when the GPUs are ready. So lots of benefits to being able to have a very fat pipe. And this is another example where our partnership with OpenAI has driven innovations into the platform because they came and said, we've got these large training runs. We have these huge models. We want very high bandwidth access to Azure storage. So we created something for them that is now available called scaled Azure storage accounts. And the idea here is that we create effectively a virtual storage account that consists of many storage accounts underneath it, any number. We can scale this to arbitrary sizes. And so this is literally hundreds of petabytes of capacity in a storage account, terabits per second of bandwidth, and hundreds of thousands of IOPS. And let's go take a look. This demo is going to blow your mind if you're familiar with storage at all. So this one, we're going to use a Cycle Cloud job to go and push 1.5 petabytes of data into a whole bunch of storage accounts. And the first thing we're going to see is connecting to one of those Cycle Cloud VMs, that it's got storage accounts mounted through Blob Fuse, a Linux interface to networking that projects it as storage. And you can see that we've got 480 nodes that are going to be executing this task of writing to data. So let's see that the right side, the write throughput. There we go, 22 terabits per second of storage bandwidth. Yeah, so some of you get that. But wait, that's the write side. Let's go take a look at the read side. And this is reading from a totally separate set of 695 VMs. By the way, that's all we could get. And this is reading to different ones so that we're not using a cache. And you can see it's red. It's like too much. Hey, this is too much bandwidth. 50 terabits per second. So back at Ignite build, I showed 30 terabits per second for this. We're at this demo, I said we need to do better. So we're at 50 terabits per second. And we'll see if we go up from there. But that's the kind of acceleration that you can get using this scaled storage account. OK, so we're in the final section of the presentation now. We've been talking about lots of innovations in the infrastructure, but one of the fundamental ones is the transformation of our infrastructure for cybersecurity. And the technology that Microsoft has been driving is something called confidential computing. In fact, if you've heard me talk about this before, we came up with the name confidential computing. We co-founded the Confidential Computing Consortium. And we worked with hardware partners, NVIDIA, AMD, Intel, to drive confidential computing into their roadmaps. And the idea behind confidential computing is that you've had protection for data in transit. That's just network encryption. And today, if you're not encrypting your network traffic, people think you're insane. Everybody wants to encrypt the communication. Encryption for data at rest has been something that in the early days of cloud, we didn't have it. And over the last 10 years, again, It's not just mandatory, but people want service managed keys and customer managed keys on top of their storage at rest. But what's been missing is when it's in use, when you read that data off the network or when you pull it off the storage, now you process it, and that's out in the open effectively. It's visible to the hypervisor, it's visible to the host software, it's visible to the operators that might connect to the machine. You want to protect and encrypt that as well, and that's exactly what confidential computing does. It not only creates this black box around the code and data that's protected by the hardware encryption, but the hardware can provide an attestation, a quote, what is inside this black box. So it measures it, produces a hash, and then signs it with a cryptographic key that's inside the hardware that can't be seen or tampered with. And then the workload can take that attestation signed by the hardware, present it to a relying party that can look at it and say, well, this is signed by an authentic AMD processor or Intel processor or AMD GPU, and so I know it's protected now, and I can release a key to it, knowing that it's protected with confidential computing, and that allows the workload then to decrypt the data inside that box, while it's inside that box, and have it protected while it's in use. We're taking a massive bet on confidential computing inside our own infrastructure. If you take a look at other products that we've enabled with confidential computing starting in 2018 when we first introduced it, we're up to this, and the list is growing literally by the month. Confidential containers in Red Hat OpenShift, confidential inferencing with Azure OpenAI Whisper, confidential containers on AKS, confidential ACI containers, and then the hardware itself, where we're, of course, deploying confidential GPUs and confidential virtual machines. This is the list, just a subset of the list of services. Our plan of record is to migrate all of Azure's core security-sensitive, trusted computing-based services into confidential computing to protect it from ourselves, to protect it from threat actors. And you can see some of the list here. Some of the noteworthy ones just in the last year, the Microsoft Payment Service, all of our credit card transactions are processed in confidential computing. Our trusted signing service now, so we can do certificate signing creation in confidential computing. And another one is the key management service, the license key management service for the Microsoft App Store. That is all running inside of confidential computing because, of course, those licensing keys are extremely valuable. But one of the things that we've also been doing is driving forward the state of the hardware security ourselves. So if you take a look at one of our boards here, server boards, we start with Azure Boost. And Azure Boost now supports things like ABCD for encrypted connections between a confidential enclave on the server and the Boost device, which then can talk confidentially or encrypted to something else. We also have a data center secure control module, DCSM, for platform rooted trust. We've got an integrated HSM that I'm going to talk more about now. And then we've got, of course, the VMs or GPUs that are running their own confidential computing. And then finally, we've got an open source silicon root of trust called Calyptra that we actually designed ourselves with working with AMD and Google and contributed to the Open Compute project, where now it's being put in basically almost all modern silicon coming out today, whether it's CPUs or GPUs or other peripherals like SSDs or NVMe devices, will have Calyptra as part of it. But let's talk a little bit more about Azure Integrated HSM, because this will give you an idea of where we're going end-to-end with provable cybersecurity and provenance. So if you take a look at Azure Integrated HSM, what it is a hardware device that acts as an HSM that we're putting in literally every single server we deploy today. The VM can create a connection to that device that can't be exposed, where the keys are sitting inside that HSM and cannot be extracted by the hypervisor or anything else trusted on that platform. The VM has the ability to use those keys to, for example, sign things or to decrypt things. And the way that the managed HSM gets those keys is that it provides an attestation, well, let me back up here, provides an attestation of its authenticity to our managed HSM, our root HSMs. And if the key release policy says, yes, I trust releasing this to this Azure Managed HSM, then the key gets transmitted to the server, stuck in the Azure Managed HSM, never leaving a FIPS 143 boundary, all the way out to the servers. And so this is what we think of like an HSM fabric that will extend across all our data center infrastructure. But where we're going with this is we want to prove things about the provenance and security of firmware, devices, and software. So one of the questions that somebody might have is, hey, I'm going to go and request a new key pair from a managed HSM. How do I know it's real? Well, the way that we do that is we actually sign the hardware attestation. And when we verify that that's really when we're deploying this thing and we verify it's a managed HSM that's ours, we sign it, and we record the fact that it was signed in something called a signing transparency ledger, which we just introduced in a preview about a month ago. And this service is where we're going to be recording evidence of everything that we do, from the software builds to the code and the policies on the code to things like our signatures. So you can now, with the receipt, get proof back that this Manicore, or this, sorry, Azure Managed HSM, Manicore is the code name for it, is actually an authentic Azure HSM 143 FIPS certified, and that your keys are protected as you use them. And then an auditor can go check that. So I've got one bonus thing to show you. We've just got a few minutes left. And this thing I had to fit in because it is one of the coolest things I've ever seen. I mean, that was a whole lot of coolness you just saw. But you're going to admit, I think, that this is really super cool. Optical computing. So what if you could do computation in light? It turns out with light, it's got all the building blocks for doing neural networks. You can do multiplication with filters. Effectively, it filters a multiplier on the strength of the light. And you can do addition by combining light. So with addition and multiplication, you can do matrix multiplication. So what if you could create a neural processing unit from optical? And that's what we've done. You can find it and more information about it in this paper from Nature. But what I'm going to do is show you this system. So you can see it's still bulky today. But the benefits of this, if we can miniaturize it and get it to the point where we can put it into production and reliably engineer it, is that it's hundreds of times more energy efficient than GPUs. You wouldn't need any cooling at all for an optical computer. So, and it's also, of course, operates at light speed. So lots of benefits from optical computing. And the key components on this thing, just to highlight one, are the projectors. That's where you do basically the multiplications. The micro LEDs, that's the light source. So these are kind of standard components. We're just putting them together in novel ways. And CMOS sensors, that's where you do your readouts. So I've got connected live from the UK, our research lab there, Francesca. Hey, Francesca, can you hear us?
Hi, Mark. Hi, can you hear me?
I can hear you. So, Francesca, do you want to show us? Do you want to show us the optical computer?
Absolutely. So let me turn the camera towards our world's first analog optical computer so that you can run the demo. Hopefully, you can see well.
Oh, okay, here I go. Somebody shout out a number. We're going to have it. 7. Okay, 7. And this is going to wake up the optical computer. And you can see it light up there. As the 7 gets put into optical signal, going through a neural network, which is a digit recognizer. And here we should see the probabilities of a 7. So its a prediction is a 7. So that came out correct. So you just saw a neural network implemented in light read my handwriting, which is amazing. Anything reading my handwriting is amazing. All right, now that it's warmed up, the second digit's much faster. Anybody have another number? 6. I think it only does 1 digit at a time, so. And now you can see the light's still on, and there we go, 6. All right, so there's optical computing. Whether this will ever be something that is commercially viable remains to be seen, but this is why we have Microsoft Research, to go explore this stuff, see how far we can take it. So with that, I hope you had a fun session. I think if you've seen ones before, you'll have to agree with me, this is one of the coolest ones in terms of all the new stuff, all the innovation, and hope you have a great night.